Hi, I'm Rielly Harrison, and today I have two rearrangements, the Hofmann and the Curtius rearrangement. So, they both involve a shift of an alkyl group onto a nitrogen, and they have a product that will be called isocyanate, which can be used to form a lot of different things. But for the Hofmann, the starting material is a primary amide, and for the Curtius, it's an acyl chloride, which you can turn into an acyl azide, which we will then do. So the Hofmann releases CO2 gas, while the Curtius releases N2 gas, and the reaction conditions are a little different. So for Hofmann, you're going to need a halogen, strong base, and heat, but for the Curtius, all you need is NaN3. So we're going to start with the mechanisms, and we'll do the Curtius first. So you'll start with an acyl chloride, which you can do nucleophilic substitution using NaN3, which will attack this carbonyl and kick that bond up. And you can reform the carbonyl and kick the chlorine off because it's a really good leaving group. And then you're left with the acyl azide. So for the acyl azide, you can rearrange these bonds to nitrogen here. So this leaving group, this lone pair will kick down onto this bond, and this bond moves onto this nitrogen. And now you're left with this, which when undergone heat will release this group as N2 gas, and you're left with a nitrene. And for the Hofmann, you have to start with a primary amide, which you can deprotonate using a strong base. So you deprotonate the nitrogen, it kicks the carbonyl up. And same thing, except for when you kick the carbonyl down this time, it's not kicking something off, it's attacking a halogen. In this case, I did Br2. So you're attacking that with the nitrogen. And here, we're deprotonating again onto this bond here, kicking this carbonyl up again, just to put it back down. This bond moves to nitrogen and the Br leaves because just like chlorine in the Curtius, it's a good leaving group. So that is now gone and we're left with a nitrene again. So the Curtius and the Hofmann both form this nitrene, but one is done with the leaving of N2 and one is done with the leaving of Br. So this nitrene is really important because this is where rearrangement comes in. So this alkyl group, and it can be anything, but in this case it's just a methyl group. This carbon here will go onto this nitrogen, which this lone pair will kick back down, and you form isocyanate. And this molecule is really useful. You can do a few things with it. You can either have an alcohol attack it, or you can do H2O hydrolysis. So for the H2O hydrolysis, you basically just attack this carbon here with water, which will kick this bond over onto the oxygen, resulting in this molecule where you can deprotonate this H on the water, put onto the N, and you're left, onto the oxygen, you're left with this, which you can then kick back down, kick this group onto the nitrogen, because it's a plus charge, so it wants to be neutral again, and you're left with this, which you can deprotonate this again. This is carbamic acid, by the way, which under these conditions is not really stable, so it's going to continue reacting. So this is going to deprotonate. You're going to protonate the nitrogen, and then you're going to kick this oxygen down, and this bond right here between the carbon and the nitrogen is going to break off, go onto the nitrogen, and you're left with an amine and CO2 gas. And for the alcohol attack, you're going to attack using the alcohol on the same C that you did before, kick this up, and you're left with this, and all you have to do is deprotonate the H, which will go onto the oxygen here, protonate the nitrogen, and then you're just going to kick the carbonyl back down, move this bond over, and you're left with carbamate. So each path will lead here. So Curtius and Hofmann will lead to this, but it's these next steps that kind of determine like what your end product is gonna be. So yeah, here are my two practice problems. You can pause and solve.